Hello, everyone. My name's Monty Weaver. My partner, Lila Stevens, was unfortunately unable to attend today, but she was, really passionate about this project, a massive help, and, shout out to her. She was really amazing. And also, my mentor, Shredayo, was really amazing during this process, and I mean, for nothing about her, she was awesome. This is my presentation on ultrasound wave-based material classification. So the general gist of this, the problem that we tackled in this project was whether it's possible to use ultrasound waves to identify different materials. Essentially, the picture we had in our mind was that someone, a human or a robot, could wear a ring around their finger, and upon contact with some sort of surface, it would send out ultrasound waves, and through those be able to identify what kind of material it was touching. Usually, we in the science world, in order to identify materials, you can use spectroscopy, but that's would be incredible overkill for this kind of scenario, and also it uses high energy X-rays, which would be dangerous to put on someone's finger like that. Whereas ultrasound is really awesome and uses high frequency sound and is completely harmless to any human. So, this was a big problem, but we started by, shrinking it down to a digestible size. We figured that we should first try the problem in a 2D sample. So we set up a simulation in which we will be able to send faux ultrasound waves through the material and then see how it would react upon hitting another material, and use this to kind of identify the way that ultrasound waves act upon contact with different materials, and therefore maybe reverse engineer that so that we could see a signal and make it a material, etc. So our methodology was basically one of 5 steps. We first began by understanding the way in which waves propagate through materials and the way in which they interact with the environment around them, especially when they bounce off of 2 materials that are different. So we learned about the math a little bit. We learned about partial differential equations, which are usually used to model the ultrasound waves that we'd be experimenting on, and then we began to build a model in order to kind of model this propagation in a simple way before we could, apply it to a greater, the greater world. So then we put all of these, we analyzed, using a computer simulation, and then we put all of our data in a library, which we then plugged into a machine learning framework, which we intended to use in order to recognize certain patterns in signals and be able to understand that signal had bounced off a certain kind of material. So first we, delved into wave propagation in general, which is basically just the way that in which waves travel through the world around them. Their energy, their waves transfer energy throughout the world using energy, and they work in multiple different ways. There's S waves, which are the more traditional, up and down motion that you associate with waves most of the time, and also P waves, which are, that cause compression of matter. And this was really important to understand in order to tackle this issue, because we were working with, wave propagation, and it's, we could understand what a certain manipulation of a point meant. If it was going up and down, it meant it was likely that an S wave was passing through it, etc. That sort of thing. So the main features of when a wave hits a new surface, when it's passing through one material and then it hits a new material, 2 things happen. If the material is stronger than the first one, then some of the energy contained within that wave passes through into the next material and keeps going the same way that it was before. However, some of that energy is lost and bounced back towards the way from which the wave came. And so the difference in the amount of energy that is bounced back is known as impedance contrast. And this was really important for our tackling of this issue. So knowing all of this, we made a computer model in which use within a 100 millimeter by 100 millimeter space, which we simulated on the computer with the properties of different materials. We then use these a computer program to simulate what would happen if certain waves pass through these materials and bounce off the boundary between them. So the computational model we use to do this is known as Salvis, which is a program made by the company Mondiac, which specializes in modeling waveforms. So we made a 2D model very similar to the one here, in which there was the top, which is there labeled as material A, was one that had the properties of human flesh, and then the second one we could change according to the kind of material we wanted to represent. So these are the properties. The computer program, in order to understand what kind of material it was simulating, needed to know the density of the material, as well as how fast P and S waves travel through that material. So this really helped it understand the boundary between the materials and how waves would react upon hitting it and passing through it. So we ran a simulation, and this gave us results like the ones you see here. And the simulation was set up like this. So there, pictured as a star, is a source from which we would simulate an ultrasound wave being generated from. And then there was 20 receivers also placed on the top, which basically acted as microphones. We could pick up any of the ultrasound which was bounced back after coming in contact with the boundary between materials. So those generated things like this. This is a signal from one of the receivers, and the motion along the y-axis there is representative of movement from that one receiver. So when that receiver moved, caused by a wave coming along and disrupting it, it would move along the axes, and this represents how much it moved along these axes. So the initial big wave is the initial wave going out, but then within the reflection window, which is highlighted in red, is the point at which the wave would come back after being reflected off of the boundary between the material. So we simulated this for wood and concrete, as well as glass. And there was differences in the ways in which the reflection window acted, depending on the kind of material it bounced off of. There was differences in the reflection maximum, so how much energy was reflected back. There was difference in the attenuation, which is how much the wave energy loses as it travels. So there would be an initial really big spike, and then it would go away really quickly. Or there's differences in rate, which meant that it kept going for a very long time. So with all of these we used, and we plugged them into a library of simulation results. Essentially what that was there was data. There's a ton of data that we got from these simulations about how many different receivers reacted upon receiving the reflected wave. So this contained all of the information about the amplitude and the wavelength when this happens. But in order to account for differences in the real world in the wave or the material that it bounces off of, we also simulated each material about 20 times with differences in the second material of up to 3%. Because we know that cypress and oak are both wood, but they have slightly different densities and properties because they're slightly different kinds of wood, and that was kind of accounting for this. So what we did with that was we plugged it into a machine learning program, which basically extracted the properties such as the amplitude or the decay, and associated those with the different materials that we had told it to associate them with. And therefore, he was able to use that to reverse engineer, basically, when it was given a wavelength or an amplitude, and it was like, okay, which of these materials is it most likely that this has bounced off of? So this is using a program called Random Forest, which basically here you can see that we give it how a certain point reacted to a wave, And then it breaks this up into multiple things. It says, okay, the amplitude here was most similar to wood, for example. And then the the highest and the lowest point is most similar to it having bounced off of steel. And if the most of the properties align with a certain material, then it predicts with a certain certainty, usually presented as a percent chance, that that material was one of the ones that we given in the past. So this is known as a classifier, which was able to take an unknown waveform and compare it to its entire library of information and spit out a predicted class of the material. So that's kind of shown here. On the left is the output for when we give it a random waveform. Here it compared it to its entire library and said that there was about a 98% chance that it was wood. After revealing to ourselves that it was in fact wood, we were like, okay, that's great because it succeeded in that. Because there were so many of its, the characteristics. So here it shows the physical measurements that were most influential in this decision-making process. So the positive to negative peak ratio was most different between the different materials. And since it was so similar to that wood, it's able to say with a certain amount of confidence that the wave that it has was one that bounced off of wood. So the conclusion here is that it is very much theoretically possible to predict a material using ultrasound waves. It was a 2D model, so this doesn't mean immediately that we can go and run and do this in the 3D world, because there's a whole lot that introduces a whole lot of other possibly confounding variables, like the sound that a ring makes when it's computing is enough to interrupt the actual computing process. Electricity creates sound a little bit. And so but we do know that a recorded ultrasound signal is not random, and it can be used to identify the things that it's passed through or the things that it's bounced off of. So we can study very specific features and predict a lot about the world, the environment that it has passed through, using just that. So we learned a lot during this process. It was really rewarding. I hadn't used computational simulations a lot before, and this was a very introductory process, but it was really great because it showed me how crucial in the 21st century specifically it is to be able to use computer programs to analyze the massive amounts of data we had, because there's so much data we got from the 120 times we cranked out numbers from each of the experiments. So it was really useful to understand how essential computer programming is to being able to tackle an issue with a scale like this one. And also, it made me realize the potential of ultrasound waves as a thing that is more than just we use to look at your unborn baby and your or it was really great. And the physical properties, to understand how such fundamental physical properties can tell you so much about the world in which you live was really great. And then, these were things I learned about the physics of the problem, about what it means to simulate, and how to use a learning model to, make predictions about the future, which I think is very fundamental to science itself. Thank you so much.
Questions?
I'm curious how much the texture of the surface affects your results. Like if you had a material but it was rough, would that change it?
Not really. It's it's the density of when it comes into contact. That might change the way it reflects off of it, because a rough surface just means that there's more ridges on a thing, even if they're tiny. So that means that they'll scatter a little bit more. But if the whole thing is the same density, they'll bounce off at the same. They'll bounce back the same amount of energy, no matter what. Yes.
Would that change if there was something like condensation on that?
Absolutely, yeah. Which is why it's very difficult to immediately change this into a 3D problem. If the condensation has a whole different set of properties. This is why they when using ultrasounds in medical fields, they put a solvent on first, so that the ultrasounds can pass through something they do know about before it actually goes into this, so they can make predictions based on it. Any other questions? Cool. Cheers. Thank you.
I was just gonna ask, do you find that this is something you want to learn more about? You have more of a window into AI than most people who talk about it all day long. So
yeah.
what do you think?
I think it was really interesting to see how it could be used. You know, I'm not like the biggest fan of AI, but like, I understand how here it's being used in a, you know, a way which is really, really, you know, in a way that I create, like you know, it's doing something that we wanted to do, and that specifically was really cool. I don't know if I'm gonna explore it a lot more. I guess I have to if I want to, you know, adapt to the way the world is changing. And, you know, especially with it's always so peace, but yeah, I think it'd be interesting to at least have this I have an understanding of like how to tackle this. Very marvelous and stuff.
Thank you.
Yeah.